Hello everyone, my name is Dmytro Heleshko, and in today's paper review I will introduce you to a paper, pretty recent paper called Drag Your GAN. In short, the goal of the proposed solution is to allow users to modify the content of GAN-generated images by moving the selected handle points to precisely reach their corresponding targets. And in order to achieve this set goal, the authors set up a list of criteria. Those are flexibility, precision, and generality, so that in the end, the solution will be able to modify a wide range of spatial features like pose, shape, and expressions on a wide range of objects like humans, landscapes, cars, dogs, cats, etc. This study in particular is based on style GAN2 architecture, and as many of you may already know, GAN or Generative Adversarial Network is a class of machine learning frameworks where two neural networks contest with each other, where one agent's gain is another agent's loss. And GANs were used extensively by our grandparents because they had no internet connection, mobile phones, and most importantly, diffusion models. But actually, in this case, the whole solution is based around the properties of the latent space. You see, the image manipulation is performed in an iterative optimization manner, which consists of two stages. That is feature-based motion supervision and point tracking. So feature-based motion supervision drives the handle points and the neighboring content to move towards the target position. And point tracking approach leverages the discriminative generator features to update the position of the handle points. And both of those steps are actually performed by utilizing the properties of the latent code. And the whole optimization process usually takes 30 to 200 iterations. So the motion supervision, during motion supervision, loss function enforces that the handle points move towards target point by optimizing the latent code W. Specifically, they use feature maps from the style GAN to hidden layers, which are resized to the same resolution as the final image via bilinear interpolation. And then a small patch around P is supervised, and the idea is to move that content towards the target point T by a small step. Here we see the formula of the supervision loss. So omega 1 of pi r1 denotes a set of pixels whose distance to pi is less than r1. F of q denotes the features at pixel q. Di is a normalized vector from pi to ti. So in the first term, for each pixel qi that is within some radius of handle point pi, we calculate L1 loss between the features at point q, at pixel qi, and the features at pixel that is in the direction of di from qi. And in case binary mask M is given, unmasked region is kept fixed with a reconstruction loss as shown in the second term. In other words, we optimize the latent space so that the unmasked region stays the same, and the content at and near the handle point pi will move towards the target point ti. Motion supervision steps moves each handle point towards its target by a small step, but the exact length of the step is subject to complex optimization dynamics and therefore varies for different objects and parts. If the handle points are not accurately tracked, then in the next motion supervision step, wrong points will be supervised, leading to undesired results. And an obvious and well-known solution to track points is through optical flow. But the authors state that using auxiliary networks may harm efficiency, and those other third-party solutions could accumulate error, especially in the presence of GAN artifacts. So they decided to implement their own solution, and they found out that the features of GANs are good at capturing dense correspondences, and thus tracking can be effectively performed via nearest neighbor search in the feature patch. And despite its simplicity, benchmarks show that it outperforms state-of-the-art point tracking approaches, including Craft and PIP, for this particular use case. And since they do not use additional networks, they achieve pretty efficient manipulation, and the whole optimization process takes a few seconds on the RTX 3090 GPU. Now, evaluation. Since the most similar model is user controllable LT, it is provided here as a benchmark, and we also can see their performance when using different point tracking solution, and they were right. Their proposed solution for point tracking works the best. And since it's a pretty new area of research, there's not much competition. So yes, that's that. Here are some examples. So in the first row, we see the inputs and the prompts. In the second row, the results from the user controllable RT. And in the third row, the results of the proposed solution. I honestly don't know why did they even provide the results from user controllable LT, because it's not trained to work with those kind of input prompts. But either way, as we can see, their proposed solution works well and the results look realistic. Here are some more examples with different objects. And here we can, in the second row, we can see how the presence of mask influences the results. And in the first row, we can see the examples of pose, hair shape, and expression editing. And also, because this solution works only with GAN-generated images, they use GAN inversion to create a copy of a real image to edit it later. And here is an official demo of their solution. So this solution, you can play around with it in Hugging Face spaces in Google Colab, or you can download the code and use the GUI that they provide. So it works in interactive iterational manner, and you can stop the optimization when you feel like it's good enough. Okay. And I would also mention that since the release of the paper in May, there have actually appeared 2 more papers which try to recreate or even improve the proposed solution by utilizing the diffusion models with, how do you call them? With intermediate features. Unfortunately, neither of them have provided both code and checkpoints, and I'm not the type of guy who enjoys training diffusion models locally. So, in conclusion, the authors have presented an interactive optimization-based approach for intuitive image editing that leverages pre-trained GAN to synthesize images that not only precisely follow user input, but also stay on the manifold of realistic images. It also does not rely on domain-specific modeling or auxiliary networks. And this is achieved using 2 novel ideas: an optimization of latent code that incrementally moves multiple handle points towards their target location, and point tracking procedure to faithfully trace the trajectory of the handle points. And in my humble, totally professional, and absolutely unbiased opinion, those interactive computer vision solutions are pretty interesting and cool because they are not only beneficial to the final users, but they can also be, or at least will become, a neat instrument in the arsenal of computer vision engineers. Actually, the first time I saw the video demo, I immediately thought of how it can be paired with a pose estimation or landmarks detection solution to automate image manipulation or even create some synthetic data. And that is all for today. Thank you for your attention.